What do this simulation of the spread of a forest fire and this simulation of the spread of a flu at your school have in common? Well, they're both grids with values in them that evolve over time, and that means they can both be modeled with cellular automata. Now let's talk about some basics. A cellular automaton is a computational model shaped like a grid of values in any number of dimensions. For simplicity, I'll be using a one-dimensional array, also called an elementary automaton. Every item in this array is called a cell, and every cell has a state. It can be a continuous state, but it's usually a discrete state, like a binary 0 or 1. Every cell also has a neighborhood. All of the cells orthogonally adjacent to this cell are its neighborhood. More specifically, its von Neumann neighborhood. In 2 dimensions, the neighborhood looks like this, and in 3 dimensions like this. But the power of cellular automata lies in their ability to change. Right now, this automaton is paused in its current iteration, but let's write some rules for preparing the next iteration. A rule is a formula for how any given cell will change based on its current state and the states of cells around it. For example, we can say for a binary elementary automaton that if a cell has exactly one neighbor with value 1, it'll become a 1 next iteration. If it has 2 1 neighbors, it becomes a 0, and if neither is true, it retains its current value 0 or 1 on the next iteration. Now, you might be wondering what happens to these end cells. A common solution is to implement periodic behavior, meaning that the end right cell is also the neighbor of the left cell, and vice versa, and it wraps around, kind of like a torus. Now let's go back to the example. Let's set initial conditions for this automaton as central cell is 1 and everything else is 0. Now let's start at the left of the array. For this example, we'll use periodic end behavior, so that means this cell has 2 0 neighbors, it doesn't change, it's still a 0 the next iteration. Next one has 1 1 neighbor, which means it becomes a 1. Moving through the rest of the cells, here are our results for the first iteration and the second iteration. Now you might be wondering, if we only had the second iteration, will we be able to tell where it came from? Will we be able to infer the first iteration? This is a reversibility problem, and in this rule there are other configurations that could lead to the exact same outcome, so this automaton is not reversible. Now, how do we formally write rules? Here are the 8 possible ways a central cell plus 2 neighbors in a binary elementary cellular automaton can look. For each of these 8 situations, we can write the next state that a rule recommends for the central cell, then collect these 8 bits into a number, the rule's Wolfram code. Our rule makes these judgments for the 8 situations, so here is its Wolfram number. For example, in the top left, the central cell is a 1 with 2 1 neighbors, meaning it becomes a 0, and that is the first bit of the Wolfram number. The size of the neighborhood and the number of possible states are related to the number of possible rules that can be constructed. This makes sense because if you remember, we had 8-bit rules representing 8 possible neighborhoods, 2 to the 8 or 256 distinct rules. And those 8 possible triads came from 2 to the 3rd possible combinations of 3 cells with 2 states each. It all works out. Now, cellular automata have really interesting applications in all fields of science, from fluid dynamics to stem cell tissue growth to pseudorandom number generators, and they're very mathematically intriguing to boot. That's all for this video. I hope you learned something cool, and thank you for watching.